OK, let's start. Good morning. So this week, we're going to discuss integral calculus. And next week, we're going to start, according to the schedule, differential forms. And differential forms is the context where we're going to combine integral calculus and differential calculus by way of fundamental theorems of calculus. Now, I want to say a couple of things. I think differential calculus we covered in great detail. And part of it is because many of the arguments that are presented in the textbook, with some minor modifications, apply to much general situations. So I thought it would be a good investment of our time and brain power to study differential calculus in this more general setting. However, with integral calculus, we're going to do it in a much less general context. And this has a couple of reasons. Part of it is pragmatic. That was part of the plan. I said I'd rather cover differential calculus in more detail and sort of minimize the complications in integral calculus as described in the textbook. Because ultimately, you have studied Riemann integration rigorously in 3210. And ultimately, at least in finite dimensions, integral calculus in the sense of Riemann is not really that much different. And then I said, well, there are certain complications, of course, but I will be sort of minimizing those complications. Because I hope you remember from 3210, once you define this thing called Riemann integration, let's say for functions taking real values defined on an interval, you get to integrate, indeed, a continuous function. But you get to integrate, in fact, more complicated functions, quite possibly. These are what are called Riemann integrable functions. And a Riemann integrable function is not necessarily continuous. So integrability is worse than continuity. And indeed, most functions are worse than continuous. But given that this is sort of, we were sort of developing C0, C1, C2, and so on, I thought it would be justified to not delve deeper into the sort of the complications coming in integral calculus. So ultimately, what I want this week is to develop integral calculus just enough so that we can do a fundamental theorem of calculus next week. Okay? So I'm going to be taking a more pragmatic approach. You don't have to do this, but trying to develop integral calculus more generally becomes more complicated. The flavor of how to define integration and stuff, it really changes. And I thought, well, we'll just do it this way. The fundamental problem in developing integral calculus in the sense of Riemann, or more generally too, in the context of infinite dimensional spaces, is that in infinite dimensions, there is no natural notion of volume. Okay? When you have a finite dimensional space, at least for some subsets, you can define an intuitive notion of volume. In infinite dimensions, this breaks down. And from a more algebraic point of view, too, when you look at linear transformations between infinite dimensional spaces, there is no natural notion of determinants. Determinant, too, is a finite dimensional thing. And so let me just say it like this. In infinite dimensions, no notion of volume or determinants is as natural as those in finite dimensions. Let me put it that way. Because there are determinants and volumes and stuff in infinite dimensions, because otherwise there would be no probability. There will be no stochastic processes and stuff like that, but we're not going to get there. So I'm just going to say no notion of volume or determinant is as natural as those in finite dimensions. This is sort of like a vague statement. In a second, I'm going to give a more rigorous, more sort of explicit thing where you could feel this. OK. So remember, we were talking about back in perhaps week 3 or something, how in 1 dimensions, it was clear what the natural nice set was supposed to be. It was an interval. It was a closed and bounded interval, in fact. And continuity in 1 dimensions was so that, well, continuous functions worked really well with this. We have things like, oh, if I have a continuous function defined on this closed and bounded interval, you have maximum principle, so the image is bounded. But furthermore, the image of this interval itself is an interval. You see, it's a subset of the same form. In higher dimensions, it becomes a problem figuring out what this nice subset is. And what do I mean by a nice subset? I mean these should be subsets over which I should be able to take integrals. OK? But what we're going to do is we're first going to figure out simple or nice subsets over which integration should be defined. Just like in the 1-dimensional setting, we're going to set up this partitioning scheme. We're going to do lower sums and upper sums. These are going to give us 2 proxies for the supposed integral of the function. We're going to take limits as the pixelation, the resolution of the pixelation gets smaller and smaller, larger and larger. And in the limits, insofar as that those 2 limits coincide, we're going to say that's the integral. It's essentially the same idea. Then what we're going to do is, after defining integrals of functions defined on nice subsets, we're going to expand our notion of what it means for a subset to be nice. OK? So I started writing these the lists. Let me start describing these things. Throughout, I'm going to be always focusing on finite dimensional normed spaces. Could be spaces of tuples, spaces of matrices, whatever, but it has to be finite dimensional. So let's start like this. First, I want to define what a standard aligned box in Rn is and what its volume is. Well, this is going to be nothing but the product of intervals. A standard aligned box in Rn, a space of n tuples, is by definition a subset of the form I1 times I2 times dot 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 times In, where each of these ij's is a closed and bounded interval. Okay? Let me write it like this. Ij is lambda j rho j. And here, I'm going to allow lambda j to be possibly equal to rho j, meaning maybe this jth coordinate could be an interval of 0 length. Its volume is, of course, going to be 0, but we'll see. So minus infinity, lambda j less than or equal to rho j, which is a finite number. Its volume is going to be, by definition, well, the product of the lengths of each of these intervals. The volume of a standard aligned box is, I'm going to write wall to the n if I want to be explicit about what dimensional volume I'm talking about. Okay, what is this? It's going to be the product, or maybe I should use j, of the lengths of each of these. And what is this? It is the max minus min. In other words, this is nothing but rho j minus lambda j. Okay, does this make sense? Right, because I'm taking something like this. Yep. Taking this box, I'm saying what is the volume of this? Well, it should be this, the length of this times the length of this times the length of this. That's what I'm saying. Okay. Now I'm going to take a box. I want to define a box in an arbitrary finite dimensional norm space, and I want to define its volume also. So this is the second item. We did this. Let me erase this one. Let V be a finite dimensional norm space let me say beta. Let's let beta to be a basis. Beta 1, beta 2, beta n be a basis. What does this mean? Let's remind ourselves. This means that each of these beta i's is one vector in V, and they constitute a basis for V. In other words, any vector in V can be written as a unique linear combination of these vectors. That's what a basis is. I'm always going to use finite dimensional norm spaces for integral calculus. A beta aligned box in V is a subset B such that if I were to use this m sub beta function that goes from V into Rn, which is this matrix representation, this is a standard aligned box in Rn. Okay, maybe in a second I can give an example. But first let me define the volume of an aligned box like this. Maybe I can just define it over there. Yeah, okay. The volume of a beta-aligned box in V is, again, if I want to keep track of this idea that this is supposed to be n-dimensional volume, I'm going to write wall to the n. B is going to be, well, it's going to be basically the volume of this box but I need to correct the distortions that could be possibly coming from, well, m sub beta itself. So I'm going to divide it by the determinant of it, more specifically by the absolute value of the determinant. Okay. So let's think about this. For instance, here's an example. So this correction factor is there so that the notion of volume works the way you would expect it to. Okay, for instance, let's think about this. Let me let V to be R2. I can choose V itself to be R2, but I could use a different basis ultimately. Why is this called a standard aligned box? Because it is aligned with respect to the standard basis, right? But let's use, for instance, beta 1 to be, well, 2, 0, beta 2 to be 1, 1. This is a basis, right? Because if I were to put these in a matrix, compute a determinant, this determinant is not 0. So this constitutes a basis. What is a beta-aligned box in R2, right? Let's give an example. So beta is a basis. Let's continue here. M sub beta goes from R2 to R2, right? And perhaps it's easier to think about the backwards direction, because this is supposed to be a vector space isomorphism. So it is invertible. In particular, it's also diffeomorphic. It's a diffeomorphism. And so if I were to have, let's say, C1, C2, its pre-image is going to be C1 times beta 1 plus C2 times beta 2. Okay. Okay. This was how we had defined this M sub beta back in week 1. How did we define it? We said the moment you have a basis, any vector here has a unique representation like this. Take these coefficients, put them in a tuple. That's how we define it. OK. And so how does an aligned box look like relative to beta? This is R2. The one that is the V. And when you think about this, you should think of V as the sort of unknown space. And when you impose m sub beta to it, you now have a space of tuples. So it goes this way. This is the R2, and this is the unknown space. This is the known space. That's how I want to think about it. Think about this. This is the mysterious space. This is the known space, or yeah, known. Meaning, here, things should work in the standard fashion. And here, things should be distorted, possibly, or could be distorted. Since a beta-aligned box here, by definition, under this m sub beta, is going to turn into a standard box, what I can do is I can start with a standard box here and look at this pre-image. For instance, what I can do is this. Here is a standard box. Okay? This is a standard box. So how would I write this? This I would write as 1, 3 times 1, 2. So this is a standard box. Standard aligned box. Okay? Any questions about this? Okay. Now I need to look at its image under this m sub beta, or its inverse rather. Here's what you can do. Well, you can just look at where the corners are sent. Because you should think, well, under linear transformations, line segments should transform into line segments. So if you can keep track of where the corners go, you know where the edges go, you know where the shape goes. Okay? And so this point, for instance, is 1, 1. In the backwards direction, then, 1, 1 is going to be sent to beta 1, beta 2. Beta 1 plus beta 2. So now we need to draw that. So beta 1 is, what was it? It is, did I not write it? Beta 1 is 2, 0. So it's this guy. Beta 2 is 1, 1. And what did we say? Well, this corner, let's denote it by a triangle. This corner is supposed to be sent to beta 1 plus beta 2. Geometrically, what does it mean to add vectors? Well, you're just going to put them sort of next to each other. And so triangle really comes from this point. Okay. Doing the same thing, for instance, I can use this corner. What is this? This is 3, 1. There it's going to go to 3 beta 1 plus beta 2. 1, 2, 3 beta 1s plus 1 beta 2 goes here. Are we happy with this? And based on what I said, under linear transformations, lines should remain lines. Well, this edge is going to become this edge. Okay, let's keep going. Let's use a box for this corner. Now, what are the coordinates here? It is 1, 2. 1, 2 goes to beta 1 plus 2 beta 2s. Beta 1, one of them, 1 beta 2, second beta 2 goes here. And of course, there's one final corner that I should add here, something like this. The remaining, let's say star, is going to go here. This is now a beta aligned box. So when I say box, because the alignment could be different, in 2 dimensions, it really means parallelogram. Okay? What is the volume? Or in this case, of course, 2-dimensional volume is nothing but area. What is the area of this standard aligned box? 2, right? Length of the base times the length of the height. What is the area of this parallelogram? Right? So the base times the height. When you have a parallelogram, insofar as you're sort of deforming it this way, it's always going to be the height, which means it's going to be base times height again. The area of this is going to be 4. There's a discrepancy. That discrepancy is exactly the determinant of this guy. In this case, what is the matrix of this m sub beta? Well, in this case, the space that is supposedly mysterious itself is known. So I can think of m sub beta as a 2 by 2 matrix. And really, this is nothing but 2011 if you want, or maybe the transpose of it. In any event, its determinant is going to be 2. So this definition is defined so that the notion of volume is compatible with what we know how volumes are supposed to transform. Any questions about this?
This is pretty cool. This is like tying into measure theory a bit.
A little bit, yes.
What I know of it.
Yes.
I saw this like great phrase, this great passage on Wikipedia about like how the Banach-Tarski paradox affects measure theory. And
yes.
One of 5 concessions must be made. Number 4 is maybe you need to change what ZFC means.
Yeah, yeah. Mm-hmm.
Yeah.
Certainly it is compatible, but we don't need to go that far in order for this to make sense. My perspective is, I know linear algebra. Whatever volumes are, they should be compatible with linear algebra, at least in the context of volumes of sort of linear algebraic objects.
Yeah.
OK. And indeed, what I want to go for is this idea that, in fact, the moment you define volumes of aligned boxes this way, or rather, more generally, both of these definitions, on the one hand, the volume of a standard box and the volume of an aligned box, these actually implicitly have the 2 most important computational ideas. First of them is U substitution. You want ultimately your integral to be so that some sort of U substitution should work. And really, this is going to be that correction factor in the integral when you do the change of coordinates. And second of all, second computational idea is Fubini theorem. This basically says, well, the volume of something like this should be, I should be able to do this in terms of iterated integrals. So somehow, n-dimensional volume should be 1-dimensional volume done n times. Okay. Any questions about this? here's a very nice exercise. This is a change of variables formula for boxes and linear transformations. Maybe I should do this here. Let's do this. This is also a review of linear algebra. I was hoping to do this back in week 1, but we didn't have time then. From this perspective of transformations of volumes under linear transformations, many ideas really come up naturally. Determinant is in fact one of them. Another idea that is rather natural is this row reduction or reduced echelon forms. So here's an example, or maybe let's say remark. Let V and W be finite dimensional norm spaces, and let's let capital Phi to be a linear transformation from V to W. Remember, by the fundamental theorem of normed spaces, any linear transformation defined on a finite dimensional space is automatically continuous, automatically bounded, automatically differentiable, everything. Everything automatically works. So differential calculus, everything works beautifully for these guys. What I want to do is this. I want to first take an aligned box in V, push it into something in W, and somehow relate the volumes of the two. Let beta be a basis of V and B be a beta aligned box in V. I want to come up with a transformation formula. I want to relate the volume of B to the volume of its image under Phi. There's a problem, though. At this stage, I'm not assuming that Phi is invertible to begin with. OK? But at the very least, what I can do is, well, it has its image, right? The image of Phi is going to be, in matrix language, the column space. Let's let R to be the rank of Phi. In this latest problem set that you're working on, there are two problems about this rank. It is nothing but, well, the rank that you remember from 2270. It's the dimension of the column space in terms of matrices. If you want to think of it in terms of reduced echelon forms, it's the number of pivot columns. You can think of it in multiple ways. Furthermore, by the rank nullity theorem, remember, the dimension of V, the input space, in this case it's n, equals R plus the dimension of the null space, or the kernel. In particular, R is an integer either from 0 to n. It's at most n. OK? I want to come up with a nice basis for the image. Because ultimately, because B is a subset in V, the image of B under Phi 2 is going to be a subset in the image. So saying that the rank of phi is R is the same thing as saying that this is an R-dimensional subspace of W. So really, I should be comparing the n-dimensional volume of B to the R-dimensional volume of its image. Okay. But there's another problem here. This phi function could be, even though it is linear, it could be rather bizarre. It could be a rotation or whatever. And in particular, if I were to just start with an arbitrary basis of W, the image may fail to be an aligned box relative to it. So somehow what I would like to do is, well, I want to come up with a basis of the image of phi at the very least in such a way that the image here is aligned with respect to that basis. In this situation, what is a nice basis for this space? What does it mean, nice here? It means it should be so that phi is nice relative to it. That is to say, its matrix representation is as simple as possible. Well, I know many of you are shaky on linear algebra. It's a good time for you to go back to your linear algebra notes. What you can do is you can take each of these vectors, look at their images. So phi of beta 1, phi of beta 2, and so on. Each of them are going to be here. And by definition, these span everything. They may not be linearly independent, but at the very least, they span. Whenever you have a spanning set of vectors, you can just get rid of some of the redundant vectors to come up with a basis. That's the idea. So let's try it like this. OK, just going to leave it as an exercise, this statement. There is there are indices increasing such that phi of beta sub I1, phi of beta sub I2, and so on constitutes a basis for the image. Now this is a nice basis, OK? Let's call this guy gamma 1, this guy gamma 2, and so on. And this gamma sub r. And this whole tuple let's call gamma. OK? Now setting up this diagram like we used to, we can come up with a matrix representation of phi with respect to these bases, this and this. I'm going to leave this to you to verify. It turns out that with respect to these two bases, phi happens to be a row-reduced echelon form. It's like even more reduced, but it's not completely column reduced. So let's write it here. What do I mean by this? I mean this. I have here v. From v, I have a phi function. But I'm not going to look at the whole w. I don't care about what is not in the image. I'm just going to think of phi to be a function from b to its image. It is a subset in w. It's a subspace. This, under the matrix representation, m sub beta, turns into Rn. This, under the matrix representation over there, relative to the spaces, turns into Rr. And now here I have the matrix representation of phi relative to these two bases. And in our notation, this was this. And when I write it like this, I mean take this matrix and apply whatever vector here by left multiplying by this guy. And when you think of it that way, it turns out, and this is again an exercise, this is going to be an R by N matrix. So it's going to be sort of elongated this way. Okay? And this is going to be essentially a zero matrix, except at I1, I2, I2, In columns, or IR columns, where you're going to have a pivot. So you're going to have a 1 here, you're going to have a 1 here, you're going to have a 1 here. Everything else is going to be 0. Okay. This is a very nice exercise. Okay? Just to connect stuff you learned in 2270 to this business. You don't really have control over I1, I2, whatever, because in principle there could be multiple choices of these indices. But those multiple choices, you see, if you were to change if you were to choose different indices, your basis for the image would change, which means that ultimately this matrix representation would change. Not the transformation itself, but the matrix representation. OK. Now, this is a very nice form, because I know by just computing that if I were to take a standard aligned box in Rn and apply this matrix to it, it's going to turn into a standard aligned box in Rr. OK? So say this box that I started with, the box in B, and I said that it's a beta aligned box, when I switch over to beta coordinates is the product of these intervals. Okay? N-dimensional volume of B, based on the definition, going to be nothing but the products of the lengths of these intervals divided by determinant of m sub beta. This is the one side. On the other side, I want to compute the R-dimensional volume of phi of B. First of all, this shows that indeed this is a gamma-aligned box, because by definition, using this coordinate chart, instead of phi, I can use this, that. Let me just call it A, this matrix. this is a standard aligned box based on the specific form of A. It is a beautiful reduced matrix. This is an aligned box. And since phi of B is, well, the preimage under a specific basis of an aligned box, it is aligned. So this makes sense. And based on our definition, this should be nothing but the r-dimensional volume of this guy divided by this, but you need to multiply. Well, OK. I can just write it like this. Determinant of m sub gamma inverse, like this. If you want to get rid of this inverse, it would be just like a number in the numerator. The final thing to compute then is, well, what is this? If m sub beta applied to B is this product, well, to compute this guy, all I need to do is I'm going to take this and apply to it this matrix. I'm just going to leave it to you to verify that if you were to take this product set, I1, I2, whatever, and apply to it this guy, you're going to be left with I sub I1 times I sub I2 times I sub IR. You see, in the pivots, you only have ones, so there's no distortion. And really, applying this A corresponds to getting rid of all of those lengths that correspond to non-pivot columns. In particular, the r-dimensional volume of this is going to be nothing but the length of the products of the lengths of these. Okay. We're almost there. So this product is almost this product, except that it's missing some of the factors. When we write this out, we're going to have a nice explicit formula between this and this. Okay. This is very important. And as you see, I'm not doing anything beyond linear algebra. But I highly recommend you sort of go through the calculations and verify that these indeed work the way they do. OK, good. Thank you. I'll see you tomorrow. OK, let's start. Good morning. So we were discussing integral calculus. Yesterday, we defined standard boxes. These were boxes, certain compact subsets of Rn, which were of the form I1 times I2 times ... In, where each of these is a closed and bounded interval. These were sets of this form. And then we defined their volumes to be the lengths of these sides. Then we said if we had a finite dimensional vector space V with a basis beta, we defined what a beta aligned box is. Namely, it's a box, it's a compact subset whose image under this matrix representation map becomes a standard aligned box. And then we figured out that really this means that, for instance, in 2 dimensions, an aligned box is essentially a parallelogram. This is the first vector, and this is the second vector. And then we defined the volume of such an aligned box to be, well, essentially the volume of the standard box, but we had this correction factor, which was the determinant of this guy. We said the volume of an aligned box like this should be the volume of the standard box, the sides, the lengths, the product of the lengths of the sides, divided by the determinant of this matrix representation in absolute value. And then I started discussing this linear change of variables formula, because ultimately the reason we're doing things this way is underneath the hood, so that we have 2 important theorems. One of them is change of variables formula. The other one is Fubini. Remember, I told you yesterday that we're taking a rather more pragmatic approach to integral calculus, and we're just going to define things so that we can do differential forms and fundamental theorem of calculus. And for computation purposes, 2 things that are very important are Fubini. I would like to be able to take apart an n-dimensional integral into n one-dimensional integrals. So maybe I should say something like this. An integral over a box should be, let's say, an integral over each of these slices, like so. So you take one of these slices, you integrate over that, and then maybe you integrate this way. That's Fubini. And then there's also a change of variables formula. Which basically says that you get to do U substitution, but quite possibly your integration, your integrand is going to change. And really, we're going to see in a bit this number that shows up in the denominator is an instantiation of this, actually. I'm defining the integral this way so that these work. This is just to bypass a lot of the complications. Now, in the textbook, they define not this, but they only define this, the volume of a standard box. But then it becomes a problem to figure out this change of variables. So compared to the book, in fact, I am assuming more as to what volume should be or how it should operate. OK, so let me remind you what we were discussing. Yesterday, I called this a remark, but I think at this stage, we can call it a theorem. Now, this is purely linear algebraic. OK, I'm not doing anything based on calculus. I'm just pushing certain things around. So let me be explicit and write down the formula that I was trying to discover yesterday. The idea is this. I want to take 2 linear spaces, finite dimensional. Remember, in integral calculus, we're just going to focus on finite dimensions for practical and deep reasons simultaneously. I'm going to take 2 finite dimensional vector spaces, V and W, let's say. And I'm going to take a linear transformation between them. Between finite dimensions, so insofar as you're considering finite dimensions, remember, linear transformations are automatically bounded linear. They are continuous. They are C infinity. They are everything. OK? So everything we discussed works well for these. I'm going to take a box in the input vector space that is aligned relative to some basis. I'm going to push it to the output space using my linear transformation. And I'm going to try to relate the volume of the image to the volume of the domain. That's what we're trying to do. So let me write this. Let V and W be finite dimensional norm spaces, phi be a linear transformation from B to W. Let's set beta to be a basis for V. Be a basis of B, and let's let B to be a beta-aligned box in V, so that I can talk about the volume. Remember, what does this mean? This means that I look at all the directions that are determined by my basis, and I'm just looking at a parallelogram or parallelepiped in 3 dimensions if you want, but it could be arbitrary dimensional. OK. The statement should be like this then. OK. Let's put R to be the rank of phi. This is the image. So this is the dimension of the image of phi. In other words, in terms of matrices, this is the rank of the matrix that would represent phi, relative to any basis, in fact. Put R to be the rank of phi. If you want to think of it in terms of row reduction, this is the number of pivots, pivot columns. OK. Then there are R distinct indices, I1, I2, IR, between 1 and n. Such that if I define, so for gamma 1 equals the image of beta sub I1, gamma 2 equals image of beta sub I2, and so on, if I were to take these R vectors in the image, put them in a tuple, and call it gamma, that would be a basis for the image. And we have let me write it here. OK. That gamma, first of all, is a basis for image. The associated matrix representation of phi relative to these is in this beautiful reduced echelon form. It's going to have one pivot at, so for instance, this is going to be the 1 I1 entry. This is going to be 2 I2 entry, and so on. So it's in a very nice shape. Third, phi of b is a gamma-aligned box in the image. And fourth, I have the change of variables formula, which is this. Okay. So I want to relate this to the volume of its image, but it's going to have r dimensions at most. So I'm just going to look at the r-dimensional volume. This makes sense because of the previous parts, but there is some correction factors that need to be included. Part of the correction, I mean, all of them really are coming from phi. Part of the correction factors come from these charts, m sub beta, m sub gamma. I'm going to write it here. And there's going to be some other correction factor coming from the fact that quite possibly r is less than n. So maybe there's some collapse happening. And so what is this? Here, there's going to be a product where j is essentially all the indices that you didn't use over there. So 1 to n, except any one of these I sub k's. And here, there's going to be two determinants. Let me try to remember. And then an absolute value. Let's write here the chart that defines this matrix. Oh, I should use the image here. This is RR. And this matrix is the one that goes over there, which means that phi is m sub gamma inverse composed with this matrix composed with m sub beta. I should be seeing here something like the determinant of phi inverse, which means I should be seeing the inverse of this, which means that in the denominator I should have m sub beta. And here it should be m sub gamma. So this is the first part. Okay. Let's also think about this for a second. Maybe I should ask you, how do I even make sense of this determinant of m sub beta? M sub beta is this matrix representation thing that goes from V to Rn. What is the determinant, or how do I even compute it? This is an important part, important thing. Without answering this question, you're not going to have a good time in integral calculus. What is this determinant of m sub beta? It came up there as well. Is this too easy of a question or too hard of a question?
Too hard.
Too hard.
I'm not 100% sure what I'm looking at. I think I've got it, but it's quite the equation.
I mean, I guess I'm asking for a sort of how to compute this. So what is this m sub beta? Let's remind ourselves. Beta is a basis, right? this m sub beta was this linear transformation that went from this mysterious space and turned it into a space of tuples. And how did it do that? It would take, so you would take an arbitrary vector in V. By the fact that beta is a basis, any V can be written as a unique linear combination of beta j's. That means that given any vector here, you have n many numbers. Well, take those numbers, store them in a tuple. That's m sub beta. Its inverse, perhaps, is easier to describe. Namely, you take a tuple of numbers and send it to the vector that is the linear combination of beta i's in this particular configuration. In week 1, we discussed how this is a linear isomorphism. Okay? So this is n-dimensional, this is n-dimensional. It's a linear isomorphism. But still, what is the determinant? How do I even make sense of this? This itself is not necessarily a matrix, or it's not presented as a matrix, right? The point is this. Even though m sub beta perhaps is hard to describe as a matrix, you can apply, again, this idea of representing this linear transformation as a matrix itself using a choice of basis. You would choose a basis for this, you would choose a basis for this, and you could write down the matrix for it. In fact, I'll leave it to you to verify that if you were to use the beta basis here and the standard basis here, the matrix representation of this would be nothing but identity. Meaning, beta to sigma, let's say, sigma the standard basis for this, matrix representation of this guy is the identity matrix. It's kind of confusing, perhaps, but this is the perhaps difference between matrices and linear transformations. And so based on this, you could compute the determinant. But you see, when I say something like this, I'm not saying that the determinant of m sub beta is 1. If that were the case, I wouldn't need to write it there. Okay? Meaning, this means that this m sub beta is not necessarily this. It's a certain representation. And how is m sub beta related to this? Well, you need to put it in this chart again. Right? So you would say m sub beta itself, this gets confusing a little bit, I guess. But m sub beta itself, you would put it here, is m sub sigma inverse times this identity matrix times m sub beta. This, of course, is identity. But the point of doing this is that once you reduce your linear transformation by choosing bases to a square matrix, then you can compute its determinant. Except the problem then is to realize that determinant should not be dependent of the basis. And that is indeed true because changing the basis corresponds to this similarity transformations, if you remember from linear algebra. Namely, because determinant is multiplicative, if you were to use a different basis, you would have PP inverse on two sides. And you could cancel these out by the multiplicativity. So it doesn't matter what the determinant is, what the basis is that you choose to compute this determinant. Determinant, the notion of the determinant of a linear transformation between vector spaces of the same dimension is independent of the basis you choose. Okay? So this is a purely linear algebraic matter. And it would be a good exercise for you to go through these, because otherwise it'll be harder to keep track of how to transform things, especially in multivariable calculus. All I'm trying to say here is that all these U substitution shenanigans start at the linear algebra level. It's really as fundamental as that. OK, I'll let you think a little bit about this, because this is sort of confusing to think about. But in any event, we have this theorem here. And furthermore, I want to add one more thing to this theorem. There's a nice case. In the case where R is equal to n, so you would say phi is full rank, or even better perhaps, phi is an invertible linear transformation from V to W. This is a slightly more specific case. Maybe we should just focus on this. If phi is invertible, which means in particular it's a diffeomorphism, and R is equal to n, it is full rank, well, this part is going to collapse. You're not going to have anything here, because you're including all the indices that are available. Because you're including all the indices that are available, and because R is equal to n, this matrix is going to be exactly the identity matrix. And this ratio is going to be exactly the determinant of phi inverse. So we have this. Okay. In other words, once we define volumes of aligned boxes this way, by certain considerations, we have the same formula for any invertible linear transformation, not only m sub betas. I think I'm going to skip writing the proof again. I was basically at the final step yesterday. I'm going to leave it to you to go through it again and do it and verify it. So let me just say exercise, prove, finish proof. What is perhaps more important is a reinterpretation of this final formula. It's perhaps easier, or maybe more convenient, to think about not dividing by the determinant, and instead taking this determinant to the other side. If we do this, we get the following. Let me do it here. So this is the important formula. Once you understand this formula, the rest is going to be a lot more clear. You see, it's purely linear algebraic. I'm going to take this to the other side and write it like so. The volume of the image of a box under invertible linear is this. Determinant in absolute value times the volume of the original thing. Okay. Initially, this is only for invertible linear. But then when you think about it, instead of R, if I were to put n here, the n-dimensional volume, and if R were less than n-dimensional volume would necessarily be 0. Right? Because a line doesn't have a two-dimensional volume. And likewise, a rectangle like this doesn't have a three-dimensional volume. Much like this, much like these, if phi were not invertible, but still it was between finite dimensional spaces of same dimension, its determinant would be 0 here. So the right-hand side would be 0. And the left-hand side would be 0 by virtue of the fact that this image is going to have less dimension than n. So in fact, this formula holds for any linear transformation whatsoever. We can leave it like this. OK. Now, the rest of what we're going to discuss, here I've written some more sort of items to discuss, is so that we can essentially interpret this in a much more general setting. Namely, I want to think of this as integrating over this image the constant function 1. And on the right, I want to think of this as integrating this constant function. Maybe I should write it like so. We're going to do this. Rather, we're going to define integration so that this is the same thing as writing this. Then we're going to replace this constant function over here by a function that is possibly not constant. Then we're going to replace this phi by a function that is only approximately linear. That's a C1 diffeomorphism. Yes?
This kind of looks like Stokes' theorem.
Um,
It bears a resemblance in appearance.
Not quite, because I'm not differentiating anything.
Well, yeah, but like.
There's no derivatives here.
Yeah.
So this is not the fundamental theorem of calculus. This is a U substitution. Yeah. Of course, in this case, I'm just integrating the constant function. U substitution doesn't do anything except create this factor. OK. Any questions or comments about this? OK, well, how are we going to develop this stuff? And I should say, this is also one of the main things, one of the computational tools of pretty much any sort of integration. You always want some sort of U substitution. And in the linear case, at least in finite dimensions, it should be true. But remember yesterday, I told you how in infinite dimensions, for instance, there is no natural notion of determinant for linear transformations. And I said equivalently, there's no natural notion of volume. So it becomes a harder thing to discuss this linear algebraic part in the infinite dimensional case, which is why we're not doing it. OK. So let's discuss aligned box partitions. So you remember from 3210, while you take a bounded function on your nice sets, then you partition the input space into smaller chunks. Based on these sort of pixelations, you have a lower proxy for the integral and an upper proxy, lower and upper sums. And then you take the limit over the partitions. Insofar as these lower and upper proxies for the integral converge to the same thing, you say this guy is integrable. You basically do the same thing here. Not really any different. Now in 3210, I spent a whole month discussing all this stuff. And so those of you who haven't taken 3210 from me might find what I'm going to discuss now somewhat bizarre. But I'm really following what I did in 3210. So definition. Let V be a finite dimensional norm space beta be a basis, B be a beta-aligned box, I'm going to define a beta-aligned partition. Let me say it like this. Finite beta-aligned box partition of B to be a finite collection of subsets of B satisfying what you would expect. Now, you should think how Riemann integration was defined in 1 dimensions, and you should keep this in mind. In 1 dimensions, we sort of like take the shortcut, usually. I haven't, but often that's what it's done. When you have a partition like this, often people focus on the cut points. Okay? So you say a partition is a collection of strictly increasing points in the interval. But really, you should think of what those cut points separate. I would like to imagine each of these boxes instead. So really, when you think about a partition, you should be thinking of these things. These are your pixels. And when you look at these lower and upper Darboux sums, you're sort of seeing the integral at some resolution. And so instead of focusing on the cut points where two pixels separate, I want to focus on the pixels themselves. Part of the reason why this is a nice thing is because this generalizes to general situations more generally. And so in the case of a box, you want to have something like this probably, right? But then how are you going to look at, like how are you going to systematically describe these cut points? There are ways, of course, but it gets more tedious. So I'm going to give a much more sort of pleasant, to my mind, description. A finite beta-aligned box partition of B is by definition a collection that I'm going to denote by curly p, is a finite collection of subsets of B with certain properties. Well, first of all, I want to have each member in this collection to be itself a beta-aligned box. So for any p and curly p, p itself is a beta-aligned box. What is more, well, I want these subsets, when I take the union of them, to give me the totality of B. So you could write it like so. And typically, when you say partition, you would have something like this, and you would say, well, the intersection of any two pixels is empty, but it doesn't quite work in this case. So we're just going to say the intersection is negligible. Nice way to say this is if I were to take two different pixels, not necessarily they are disjoint, but at the very least, their interiors should be disjoint. Interior in the sense of metric spaces. For any P1 and P2 and the partition, well, we can say P1 is a distinct pixel if and only if their interiors are disjoint. Another way to say this is, if you were to take two partitions that happen to have a non-empty intersection in their interior, then that means that really you're using the same pixel. So there's no overlap in a sense. There's no significant overlap. They could overlap, but if they do, it's going to have zero volume. It's not going to matter. Okay? Any questions about this? Now, in one dimensions, this definition matches as well. In one dimensions, what would you have? Well, one-dimensional aligned boxes are nothing but closed and bounded intervals. And I'm saying I'm going to have finitely many subintervals of my interval such that if they intersect only at the boundary. In the one-dimensional case, the boundaries of intervals consist of all the endpoints. Okay? So this matches with the one-dimensional definition also. Okay. I'm going to denote by par sub beta of B to be the collection of all partitions. Okay. Because I want to think of these lower and upper sums as, well, as a function of the partition. Okay? Let denote by par sub beta of B the collection of all finite beta aligned box partitions of B. Just like in the one-dimensional case, the moment you look at this set of partitions, you realize there's this notion of refinement. So if I have two such partitions, say P refines Q if any pixel in P is a subset of some pixel in Q. Okay, so I like to call sometimes these partitions pixelations, and each set in any one of these pixelations I would like to call a pixel. That's how I sort of visualize this. Say P refines Q if for any P in P there's a Q in Q such that P is a subset in Q. Okay. Let's give an example perhaps for this. Let's take a standard box, something like this. Okay. Now I need to chop this B into smaller boxes, but I don't get to sort of distort the directions. So each edge is going to be either horizontal or vertical, assuming that this is also like that. Okay. Maybe a different color, actually. This one. So the P partition, I like to sort of draw it like so. I want P to refine Q. OK, but let's start with Q then. Q is going to be this partition. OK? This is my Q partition. I have this many pixels, 1, 2, 3, 4, 5. Their shapes are different, but in one-dimensional Riemann integration 2, you allow different sort of like partitions. It's fine. Now P is going to have the same boxes. I'm going to try to be as accurate as this is, so something like so. But I say, so this itself is a refinement of Q. But in principle, what you could have is, you could have finer pixels. Okay, so now this guy refines this guy. Any pixel here is included in some pixel there. Okay? And how am I imagining this? I have higher resolution now. Okay? Which means that, for instance, if I were to look at a higher resolution pixelation, my lower Darboux sum should increase. This is, of course, true that you've proven this in one dimensions. The same is going to work in higher dimensions also. Does this make sense? Now, this is not, so this refinement is not as nice as something like less than or equal to for numbers, because there could be partitions that you cannot quite compare in this way. So let's look at, for instance, R. This is going to be this partition. So for instance, here P refines Q, Q does not refine R, and R does not refine Q. But there's something called common refinement. Namely, there is a refinement that refines both this and this. Well, how would you come up with that? I'm going to leave it to you because I think I'm running out of time a little bit. Well, you would take this picture, superimpose it on this picture, and that would give you a refinement, a partition that is finer than both this and that. That would be what is called the finer common refinement. How do you call it? Finest common refinement. That's what you call it, yes. So in 3210, I described all this in one-dimensional setting too. And I would recommend, if you're not familiar with these ideas, to go back and watch those lectures. But in any event, this structure then, these collection of aligned boxes together with the notion of refinement gives you what is called a directed set. Okay? And it turns out that just like integers, over which we take sequences and subsequences and convergence and stuff, over directed sets too, you can take sequences. People call these nets. And really, when you fix f, lower Darboux sum is a net parametrized by partitions like this. It's not going to matter too much if you're not familiar with this idea. But I'm just going to leave it to you as an exercise, because the proof is exactly the proof that I did in one dimensions. It's a directed set. Now, once I have a bounded function then, taking real values, and if I were to fix a partition like this, I can define lower, upper Darboux sums. Let me define that as well. Be an aligned box f. The bounded function taking real values defined on B, and P be a beta-aligned partition of B. Then, much like in the first one-dimensional situation, the lower and upper Darboux sums of f relative to P are well, what do you do? Each of these pixels have its well-defined volume. That's going to be the, instead of length, I'm going to use volume. And instead of so for the height information, I'm going to use f. I'm going to sample. And how am I going to do this? I'm going to restrict f to this pixel, and I'm going to look at the inf. If I were to use, instead of the inf, if I were to use sup, I would get the upper Darboux sum. OK. And I'll leave it to you to define a Riemann sum as well. Riemann sums require one more piece of information, which is what is called this sampling function. You need to pick from each of these pixels a specific point, and that gives you a Riemann sum. OK? The rest of the theory is going to continue the way you're expected to. Thank you. I'll see you tomorrow. OK, let's start. Good morning. So today we're going to keep working on integral calculus. Yesterday after class, I had given an exercise about computing this determinant of this matrix representation isomorphism. And then I kept thinking about it, and I realized that it doesn't quite work the way I stated. So it's a lot more complicated. I can still make sense of this in a nice manner. But even then, if we keep sort of keeping the definition of the volume of a beta-aligned box the way I defined it on Monday, it's going to give a more general integral, which I don't want. So even though technically it's not a mistake what I said, it's not wrong, you might as well take it to be a mistake. What we're going to do is we're going to discard the definition of the volume of a beta-aligned box. And we're going to discard this linear change of variables formula. And I'm going to restate them, assuming more. Namely, we're going to assume instead of merely having a norm space, we're going to assume a finite dimensional inner product space. Because otherwise, we don't really have a notion of orthogonality. And in my intuition, I want to keep this idea that if I have a sort of orthogonal box, its volume should be the product of the lengths of the sides. I want to keep that, and because of that, I'm going to assume more. Okay. I want to be clear. This wasn't. I wasn't intending this. Earlier in the semester, I did make mistakes, which I had planned, as you probably could guess. But this was not something I had planned. I apologize for this. And part of being a mathematician is, even though it hurts to admit, when you notice you made a mistake, you got to admit it. Okay. I apologize for the inconvenience. Okay. Any comments or questions? Yes.
If I wanted to learn the more general theory, what would be a good term to look up?
Probably I would call this a Haar measure.
I think I saw that once in a first looking integral where you had d to the power of Cartesian products.
Yeah. So this, if we keep working this way, it's still going to work, and it's going to give you some sense of volume. It's going to be translation invariant. That's one notion of naturalness, but it's not going to be basis independent. It's going to be basis dependent. Yeah. Yesterday I noticed this because after class yesterday I gave a makeup, and during the makeup I was thinking about how to rectify this, and is it really a problem and stuff like that. And then afterwards I started editing the video, and then I cringed so hard. It's like, this is wrong. It's not going to work as nice as I thought it would. But anyway. And then I remembered I was taking a statistics class a long time ago. And the professor did an example. I don't quite remember the example, but it had to do with ice cream, okay? It was like a word problem. And I had pointed it out, the thing, he was counting something and you get the probability of something or something. And I told him in class, this doesn't work. And he was like, no, it works. And he just like, couple weeks later, he was like, when we were like, in a private setting, he said, oh, you were right actually. But he never made the announcement to the class. So the class was like, oh, the dude was wrong, meaning me. But anyway. And part of it also is that I was thinking about this. A lot of mathematicians, I think, become mathematicians because they dislike being wrong. They really like being right. And it hurts to admit when you're wrong. Paradoxically, perhaps. But anyway, I hope I made a big enough fuss about this mistake. Now we can continue. So what we're going to get rid of is the notion of the volume of a beta-aligned box. I'm not going to use this guy because this is not well defined for us. Okay. The beauty of integration theory is that it's sort of like modular. You can sort of take one part, get rid of it, and like replace it by something else. Lower integrals, upper integrals, and stuff, they're all going to work the same. But still, what I'm going to do is I'm going to assume that V is an inner product space so that I have the notion of orthogonality. Okay? Why do I want to do this? And by the way, this example I gave on Monday too is going to work just as well. And ultimately, underneath, determining that this determinant is well defined is essentially defining a certain inner product underneath the hood. So it's actually not that different, but never mind. The reason why I'm choosing to begin with an inner product is because I want the following intuition. I would like to be able to say, if I have a box like this, in other words, if I have a beta-aligned box for beta orthogonal, right? This is the first basis direction, this is the second basis direction, let's say. Well, the area of this should be the length of this times the length of this. That's first what I want to say. Second, I would like to be able to say this. If I have an oblique rectangle or parallelogram, meaning now this is a beta-aligned box for an arbitrary basis, let's say. I would like to be able to say, well, the area of this is the length of the base times this height. How am I going to make sense of this? Well, in the general norm space situation, you cannot quite make sense of this height. But if you have an inner product, well, you have what is called an orthogonal projection. You would have, do you guys remember orthogonal projections?
I think it came up in a problem set. At least it came
Yeah, I mean, in problem set 1 too, but in 22.7 you should have covered this. OK. So if I have beta 1 here, I look at the span. That's a one-dimensional space. I look at its perp, orthogonal projection, orthogonal complement. All right, so this is span of beta 1 perp, collection of all those vectors that are orthogonal to beta 1. And so what I can do is, well, I can take this guy, orthogonally project it to get a vector like so, and then say, well, the area of this guy, the oblique shape, it should be the same as the area of this guy. So in order for my notion of volume to work, based on this intuition, I need an inner product. Okay? So this is one of those instances where we're sort of restricting our scope. What I did before technically is not actually wrong, but it gives you a more general thing. But if you're doing something more generally, quite possibly it's going to be more technical. It's going to be harder to compute things. You're going to have more things to worry about. So it's always a trade-off. It's not always a good idea to generalize things. In differential calculus, we sort of kept it as general as possible. We could have gone further, but it was certainly a lot more general than the textbook. Here, I'm sort of restricting what I started. OK. So I'm going to assume that V is a finite dimensional again. Remember, finite dimensions because even beyond this normed space, inner product space, whatever, the moment you have infinite dimensional spaces, notions of volume become a lot more complicated. So we're not doing that. As usual, as before, I have a basis beta. And beta-aligned boxes, they're defined the same. I'm not saying discard the notion of a beta-aligned box. That is OK. What we're going to update is the notion of its volume. We had defined this. We're going to change that. And so what does this mean? B is a subset such that under this matrix representation map becomes the product of n compact intervals. And if you write this out explicitly without referring to this m sub beta business, this would be just this. It's a set of those linear combinations. Beta i's are my vectors in the basis. And ci are numbers. For each I, ci is going to be restricted to come from I sub I. It's the same thing. I'm not changing the definition. I just reiterate it. Any questions about this? So now what we can do is this. Depending on essentially the configuration of beta, I'm going to define the volume of this B without sort of comparing it to the volume of this guy. The volume of this box is going to show up in the formula as well, but we'll see. Another thing I want to say about these mistakes is relating this to this idea of differentiable proofs I mentioned. There is something very interesting about mathematics, which is that historically speaking, a lot of big mathematicians in their sort of arguments, in their papers, have many mistakes. These mistakes are local, but somehow the total argument seems to work. So they had the right idea, but they had some mistakes here and there. So even if something is, from a logical point of view, a mistake, in general, it may not be that important. OK. I'm not trying to minimize my mistake, but I come from a lineage of mathematicians who are very hard to sort of pin down. OK. Define the volume of B as follows. This is going to be a piecewise definition, even though they are compatible with each other. Well, first of all, if beta is an orthonormal basis, meaning if each of these vectors are normalized and they are orthogonal, then this is going to be nothing but, well, the volume of the box, the standard box. Is orthonormal. OK? So this is the best case. My different vectors are orthogonal to each other. I should be able to just multiply the lengths coming from each side. And each of these lengths are these. And I don't need to change these lengths because each of the vectors in my basis are of unit length. If I have an orthogonal basis, meaning the basis vectors are orthogonal, but not necessarily orthonormal, they are not necessarily unit vectors, then I need to change each of these lengths by the appropriate length or norm. times beta j in norm orthogonal and finally, if beta is an arbitrary basis, well, essentially what I want to do is I want to turn it into an orthogonal basis by using sort of Gram-Schmidt. Meaning, I'm just going to do the spanning business. So this would be the orthogonal projection of beta 2. Oh, let's say this is the beta 2. Orthogonal projection of beta 2 onto the span of beta 1 perp. So I would write it like so. And so instead of adjusting these lengths by the original basis vectors, I should be adjusting them by the projections. So I'm going to denote it like so. Beta j tilde in norm if beta is arbitrary. Where, let's write it there. So what do I need to do? I need to take the beta j vector and orthogonally project it onto the orthogonal complements of the span of the previous vectors. So proj, span, beta 1, beta 2, dot, 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 beta sub j minus 1. So that's a subspace now. Look at the perp of it. That's another subspace. Orthogonally project the jth vector. This is like a geometric way of defining this. If you want an actual formula in terms of the inner products, I'm sure you can do this, but after thinking about it a little bit, but the formula turns out to be this. What is it? bj against bk divided by beta k norm squared times beta k. That's the formula. Have you guys seen something like this before? OK. Yeah, in 22.7, you were maybe not doing a very good job discussing inner products, dot products, orthogonal projections, all that stuff. OK. If this is confusing, you might as well just say, I'm not going to look at arbitrary beta-aligned boxes. I'm just going to look at boxes that are aligned relative to some orthogonal basis or orthonormal basis. Then the formula becomes a lot easier. And in fact, these are all, these can be represented by the same formula, like so. And this might show up in the next problem set, because this is a very nice exercise. For beta a basis, define its Gram matrix. Well, it's the matrix that is sort of underneath Gram-Schmidt. Define its Gram matrix. G sub beta to be the n by n matrix defined by, well, you could say correlations. So in the ijth entry, what I'm going to do is I'm going to take the ith and jth basis vectors from beta, hit them against each other using the inner product. That's going to give me a number. And I'm going to store that number here. Then it turns out that in any of these situations, volume of B is nothing but this. This is a standard case, but I need to have this correction factor in case beta is not orthonormal. And what is that? It's the determinant of g sub beta in square root. As a simple exercise, if beta were orthonormal, this would mean that g sub beta is the identity matrix, because I and j are orthogonal. If I is not equal to j, this would give you 0. And on the main diagonal, you would have beta I against beta I. That is beta I normed squared. But if beta is orthonormal, norm is 1. Norm squared is also 1. And so in the orthonormal case, this would just be 1, and so on. It would drop out. Perhaps a nicer exercise, more pleasant exercise, is to verify that for an arbitrary beta basis, if you run Gram-Schmidt to it, it's essentially about this g sub beta. So somehow the products of all of these norms end up being the square root of this determinant. It's a nice exercise. Purely algebraic. OK. So this is the definition we want to keep. OK. I hope we're not going to need to change it again. And if I can find some time, I'm going to try to write some notes, at least sort of like an executive notes about executive summary about integral calculus. So this is how we replace, or this is how we replace the volume of an arbitrary beta aligned box. And how do you replace, how do you change the change of variables formula in the linear case? Well, instead of having this determinant of m sub beta, you're going to have to use these matrices, these determinants. Now, let me reiterate. Even in the abstract setting, once I feed to this inner product two vectors, this is going to give me a number. So this g sub beta truly is a standard n by n matrix. OK. So let me say with this definition, linear change of variables for aligned boxes becomes I would think. So I want to relate the r-dimensional volume of the image of a box like this under my phi, just like we discussed. From this beta, I start with any beta whatsoever. And I apply my phi function to it. That gives me a spanning set of vectors of the image. From that, I sample out a basis, which I call gamma. I'm not going to write it again. We had done this yesterday. And I'm going to relate this to the n-dimensional of the n-dimensional volume of the original box. Let me think. The common factors are going to be these guys, which means I should be putting beta in the denominator. Yes, that is correct. So this is going to be determinant g gamma divided by determinant g beta in square root. And then I'm going to have 1 over lengths of intervals that I didn't use in this in these situation. So these I1, I2, IR were the indices that went into this image basis. You should ask yourself here, does this square root always make sense? Well, yes, because it turns out that this g sub beta is what is called positive semi-definite, which means that its eigenvalues are always non-negative, which means that its determinant is non-negative. So that square root is a real number, non-negative real number, positive real number, actually. In particular, if r is equal to n, this part drops out, and this turns into the determinant of phi in absolute value times the volume. That this turns into this is also a very nice exercise, which you might see in the next problem set, actually. OK. And so how do I think about this? I say, well, if I'm trying to look at the volume of the image, I'm just going to distribute, in a sense. But the cost of distributing the volume is, instead of saying volume of phi, you just write determinant in absolute value. That's how I'm keeping this in mind. OK. So this business is all about linear algebra. No sort of calculus is involved here. You can involve it, of course, but you don't have to. OK. Any questions or comments about this? Don't worry too much, because often we're going to use boxes that are really orthogonal. So really, when it comes to the volumes, this is the formula we're going to use almost always. OK. OK. So let's go back, keep writing more definitions. We had defined lower and upper Darboux sums, and this collection of partitions. So finite dimensional inner product space, beta B, a beta aligned box for some beta basis, for some basis beta. Recall, we took a function that is bounded on B, taking real values, and we took a beta aligned partition of B. This was a collection of pixels that were of the same type, right? What's going to be important is, well, I want my smaller pieces to be essentially of the same type as B. And what do I mean by this? If I start with something like this, I don't want to sort of chop it into rectilinear pieces. I want to chop it like this. I want all of my smaller pixels to be aligned with respect to the same basis. This is purely for convenience, really. Okay? We defined the lower and upper Darboux sums So these are supposed to be proxies for the supposed integral of f. Okay? I'm saying I cannot see sort of infinite resolution, but I can see resolution coming from this collection of pixels. I cannot see any further. F could possibly, given any one of these pixels, be fluctuating, but I'm just going to fix one value for each pixel and add those pixels, those values up. So this is what I wrote yesterday, and one of your colleagues after class asked what this means. This means I'm not thinking of f as a function of b, or on b, I'm restricting it to p. So now, infimum, quite possibly, what happens? So over smaller sets, infimum gets larger. So maybe this is not the absolute minimum, in a sense. If you want to be more explicit, this is nothing but this. Infimum of f of x as x varies in this particular pixel p. This is my height information. My base information, base volume information is going to be the volume of the p. That's the lower Darboux sum. Upper Darboux sum is the same thing, except that instead of an inf for the height information, I'm going to use a sup. So this is going to be a proxy from within. This is going to undershoot. This is going to overshoot. Okay? And in the final 2 minutes or something, I also defined something called the Riemann integral, or Riemann sum, rather. In case you haven't seen it when you guys discussed this business in 3210, Riemann sum is really the original definition that Riemann came up with for Riemann integration. The reason why these are called Darboux is because someone named Darboux came up with them after Riemann. Partially because these are slightly more convenient to use. But the point is, for a Riemann integration, remember from Calc 1, you don't use inf or sup, whatever. You use perhaps the left-hand points in the case of an interval. And so you have something like this, let's say. You chop this up. Maybe you just use these points. You don't care if these are the min or max, whatever. Or you can use the right-hand points to come up with the heights, or you can use the midpoints, depending on the, what type of function you're trying to integrate. From a numerical point of view, of course, the convergence stuff matters, but from an abstract point of view, ultimately it shouldn't matter insofar as the function is integrable. It shouldn't matter how you sample the points. But it's a certain information that you need to include. So if s is a function from the partition into B, such that for any p and p, s of p is in P. So you see, I have a bunch of pixels. For each pixel, I'm specifying a specific point in that pixel. I'm saying this is like this. I have 1, 2, 3, 4, 5, 6, 7, 8 pixels. each of these is a capital P. The collection of all of these is the curly P. S of P, let's say, is something like this. It chooses specific points. Maybe these points. Okay, this is S. You sample points for each of these, and then you're going to say, well, I'm going to feed these points into F, and that's going to give me my height information. Instead of using inf or soup, you sample one point from each of these pixels, feed those pixels into F, use those heights as your proxy. Define the Riemann sum by, well, now it's going to depend on f, p, and the sampling function s. This is my height now, and then again, I'm going to use the volume of the associated pixel. Call it a pixel, but for instance, in 3 dimensions, probably you want to call it a voxel or whatever. These have different names. Of course, it should be clear at this point, lower Darboux sum should lower bound any Riemann sum, and upper Darboux sum should upper bound any Riemann sum again, right? Because given any pixel p, this is lower bounded by the inf of f restricted to p, and upper bounded by the sup of f restricted to p. If you've taken 3210 from me, you've also seen exercises like, oh, if I were to take this and take the infimum over all samples, you get that. Take the sup over all samples, you get this, and blah, blah, blah. The stuff you expect work the way they do. Another thing, for instance, if I were to refine my partition, lower Darboux sum would increase quite possibly, upper Darboux sum would decrease quite possibly, but no lower Darboux sum is going to be larger than any upper Darboux sum. These I'm going to leave to you as an exercise. These are verbatim, so the proofs are verbatim what you discussed in 3210. Let's say Q refines P. So the pixels in Q are smaller, okay? You have higher resolution. If you have higher resolution, your lower proxy should get better quite possibly. Then I have this. I refined. I have a higher resolution thing now. Lower Darboux is going to increase. But it's never going to be any larger than upper Darboux. And upper Darboux should decrease. This says that if you were to take these guys, and if you were to take the sup over all partitions, this could only increase, and it would be well defined because it is upper bounded. The sup of lower Darboux sums gives you the lower Riemann integral. The inf of upper Darboux sums give you the upper Riemann integral. So this is, again, something common that we do in math. You do sort of like minimax. Inside the lower Darboux sum, you have a min. You maximize the min, and then you minimize the max to get the upper Darboux sums. And you want these to coincide ultimately for Riemann integrability. Write it there. Okay, I'll define. Lower integral to be this. An upper integral to be the inf of the upper Darboux sums. Call, so this is always less than or equal to this. Call f integrable if they are equal. So f is Riemann integrable on B if this is equal to that. Okay. Now, much like in the one-dimensional case, the theory works in a standard fashion. You would say things like, oh, f is Riemann integrable if for any epsilon there's a partition such that each pixel in that partition has diameter at most epsilon, and the difference between upper and lower Darboux sums relative to that partition is less than epsilon. You would say if f is Riemann integrable, then relative to any sampling function, the Riemann integrals are going to converge. For each pixelation, you're going to have to choose one sampling function. What else? Continuous functions are Riemann integrable. Product of two Riemann integrable functions is Riemann integrable. These are all standard statements I hope you guys are familiar with from 30 to 10. They all apply in this case. Okay? And the proofs are essentially verbatim the same. Not really any difference. And I don't want to waste your time rewriting the same stuff. What else? Well, of course, the collection of Riemann integrable functions is a vector subspace of the space of bounded functions. It is also closed. That is to say, the C0 limit, uniform limit of a sequence of Riemann integrable functions is Riemann integrable. And on the space of Riemann integrable functions, integral is a bounded linear operator. These are all things that you have proved in 30 to 10. Maybe you didn't use this notation, this symbol, or this terminology. But now that we know all this stuff, we can just compress all this. The collection of all Riemann integrable functions on B taking real values. It's a bunch of exercises. Just going to write them down. Oh, let's start with this. This is a closed vector subspace of this space. C0 closed. Linear subspace. C0, the collection of all continuous functions, B is compact automatically, so this is also continuous and bounded functions, is a subspace here. And integration on the collection of Riemann integrable functions is bounded linear. And of course, its operator norm is nothing but the volume of B. Okay. Maybe it would be a good idea to sort of think about what these statements should mean, how one should prove it, and match it with the stuff that you discussed in 3210. Okay. So for instance, when I say here the collection of Riemann integrable functions is a C0 space, a C0 closed space, that really means this. When you open it up, if I have a sequence of functions that are all Riemann integrable, that converges uniformly to some other function, that uniform limit 2 is Riemann integrable. Saying that this is C0 closed means that. Saying that integration is bounded linear means that if I were to take a sequence of Riemann integrable functions that converge uniformly to some function, then the integrals too should converge.
Is this like the same as saying it's a complete space?
Well, it is a complete space, but it's not the same thing as saying that it's a complete space.
Sounds similar.
Yeah. I mean, part of it is because the space of bounded functions is complete, and any closed subset of a complete space is complete. Yeah, you can say that too. Yeah. Okay. What else? Well, for instance, if I have a function that is Riemann integrable, its absolute value too should be Riemann integrable, and you should have the standard bounds. Let's write it there. So more exercises. So if, let's use lowercase phi is continuous and f is Riemann integrable, then phi composed with f is Riemann integrable. In particular, choosing as phi the absolute value function, we have that the absolute value of a Riemann integrable function is Riemann integrable, and in this case we have this nice bound. Namely, the absolute value of the integral is upper bounded by the integral of the absolute value. What else? Product of any two functions is Riemann integrable. Well, f times g is Riemann integrable. But of course, the product of the Riemann integrals is not the, the Riemann integral of the products is not the same thing as the product of the Riemann integrals. Right? So you cannot just split the integral of a product willy-nilly. You would need to use something like an integration by parts. There is, again, integration by parts here, but for that we need to go back to differential calculus to discuss further. Okay. So what you should get from this is that Riemann integration works pretty much the same way. You expect it to work based on your understanding from 3210. It all is the same. Okay, standard stuff. I don't want to waste your time because it's kind of boring to this stuff, to be honest, at least for general purposes. So we'll leave it at this. On Friday, we're going to continue with important theorems. Thank you. OK, let's start. Good morning. Today, we're going to keep working on integral calculus. We have a couple of things we need to discuss. So I'm going to be taking attendance today. So what's mainly on the docket for today is, well, mainly three things. First of all, let me write it here perhaps. We need to extend our understanding of what a nice set is. That is to say, we need to be able to integrate functions defined on more complicated sets. Ultimately because, well, we would like to be able to use diffeomorphisms to do change of variables. But then under a typical diffeomorphism, an aligned box turns into something not a box, right? So if I had, for instance, the polar coordinates, what is a box under the r theta coordinates turns into, in the rectilinear coordinates, something more skewed. So if this is the r theta coordinates under the polar coordinates, this turns into something like this. So this is the radius, and depending on the angle here, you cover something like so. You cover a wedge like this. Right? So ultimately, we would like to be able to make sense of what it means to integrate a function over something of this form. And this then is going to require us to understand what the volume of a nice set in this more generalized setting is also. And that's going to lead to this notion of Jordan content. This will be something like a volume. And we're going to call these nice sets Jordan contentable. Sets whose Jordan content exists. That's the first thing we're going to do. Related to this also is the idea that everything we developed so far really depended on the basis, was dependent on the basis that we had chosen. We always took a basis first for the space, the inner product space. And then we took a box that was aligned with respect to that basis. And then we partitioned that box into smaller boxes, again aligned with respect to that basis. But ultimately, when you're measuring the volume of something, it shouldn't matter how you measure it, ultimately. The number could be different in terms of sort of units and stuff like that. But it shouldn't matter how you sort of chop this. If you chop it like this, if you chop it like so, it shouldn't matter. It's a pound of beef, pound of beef. Okay? If you run it through the meat grinder, it should come out as 1 pound. It doesn't matter how. So we need to somehow figure out why this stuff is not basis dependent. Turns out to be related to this. So let me write that as item 2. And this was also the reason why I changed the formalism that we had started with in the beginning of this week. Remember, in the beginning of the week, we had started with a finite dimensional normed space. And then I said, well, This is not going to be as convenient, even though it is not technically wrong. It's not going to be as convenient ultimately because of this. And then the third thing is, well, so far we discussed how to integrate functions that are scalar valued. But maybe some of you remember from Calc 3 or something, there are things like centers of mass. If you have an object, and if you have a density function on it, you should be able to compute its center of mass. But center of mass is going to be a vector. So that means that we should be able to integrate vector-valued functions also. And that's the third thing we need to do. Did you guys sort of compute things like centers of mass in Calc 3 and stuff? Moments of inertia, these kind of things? Maybe, kind of. OK, so there are certain unsigned integrals whose outputs are vectors themselves. Right? So if I give you sort of a box like this, and if I were to tell you a density function, let's say this part is like more dense, more heavy, and this part is less heavy and stuff, the center of mass would not be this vector, right? It would probably be more toward this. So in the next problem set 2, that's going to be uploaded today, you're going to probably see a bunch of problems about this centers of mass. But OK, any questions before I continue? OK, so let's first handle this item 1. And the idea is this. Remember, we came up with this linear change of variables formula for boxes and linear transformations. We said, well, the volume, n-dimensional volume, let's say, of the image of a box under a linear transformation should be the volume of the box times determinant of the transformation in absolute value. And again, let me reiterate, the fact that there's absolute values here means that this change is always a non-negative number. Okay? So volume never becomes negative. In other words, what we're discussing is unsigned integrals. These are not signed integrals. And I wrote something like this. I said, well, I want to build a theory so that I can think of this equation like so. This is the integral over the image box of the function that is constantly 1, dy. And here, I want to integrate over b the function that is constantly determinant of phi in absolute value. OK? Now, especially in the context of integration, we would like to be a little bit more specific. Because technically, this function is defined everywhere, the function that is constantly 1, but we're integrating it only over this specific thing. And so another way of saying this would be, well, instead of writing it like so, I'm going to say this is an integral over the whole space D of a function that is 1 on this box and 0 otherwise. OK? And this is denoted like so. Y. And this is what is called a characteristic function, or indicator function in probability. So let me just define this. This is very general. If I have a set, so let X be a set, S be a subset, then the characteristic function of S, or in other words, the indicator function of S, these are both the same things depending on their field, is the function taking real values defined on X that takes the value 1 on S, 0 otherwise. So it's a switch. Characteristic or indicator. Of S is chi sub S, chi for, k, characteristic, that takes an X and gives you back 1 if X is in S and 0 otherwise. Now, in more applied contexts, characteristic functions mean different things, and therefore they use indicator. And instead of writing chi, they often use like a 1 or something. So maybe like 1 with a sort of the dash. Okay. And what does this do? It basically does the following, right? So if I have, let's say, an interval, gives you 1 on it, 0 elsewhere. Okay. And so now with this understanding, I hope you would agree that we have some hope as to generalizing. And this is where things are going to get slightly more technical. I'm not going to discuss how to prove things, but I'm going to give them as exercises, and I'm going to tell you when they're going to be sort of painful to prove. OK. So now, going back to our regular setting, V, again, is a finite dimensional inner product space. So I can, at the very least, integrate over boxes, and I can talk about the volumes of boxes. Let now S be a bounded subset. If I have a bounded subset in my inner product space, let me also take a basis. Of V. If I have a bounded subset in my space, well, I should be able to find a box that is aligned relative to this basis that I chose that contains my whole set. Okay? You can say, well, a bounded set is included in a sufficiently large ball centered at the origin. And then if you have a ball, you can sort of encapsulate it in a box if you want. What I'm saying is this. S is something like this. And I'm taking a large enough box. Okay? And I'm going to think of, instead of S itself, I'm going to think of its characteristic function. And I'm going to try to integrate it over this box. So let me write it like this. S be a bounded subset, beta be a basis, and B be a beta aligned box with S inside. Then the lower and upper Jordan contents of S are defined as the lower and upper integrals of this S. Or maybe I should say inner or outer. That's better, perhaps. Inner and outer Jordan contents are defined, by, I'm going to write jor, okay, with an underscore. So this is going to be the inner Jordan content, n-dimensional. I'm going to define this to be the lower integral of the characteristic function of S over this box that I chose. Okay. And likewise, upper Jordan content is going to be the upper integral. Remember, so first of all, a characteristic function is always bounded, right? It takes either 0 or 1. It's a bounded function. And whenever you have a bounded function defined on a on an aligned box, its lower and upper integrals are well-defined numbers. I'm not saying anything about whether or not these two things are the same number, but these certainly always exist. Okay. Now you should be suspicious of this, and you should ask, well, does this depend on this B that was not included in the definition of S? I just took a subset. It was a bounded subset. And I just found some box with respect to some basis that was like large enough. And this is where things get more complicated, you see. It is true, and I'm going to leave it to you as an exercise, that indeed this expression is independent of B and the beta. And likewise, this is, maybe these are not actually, hang on. We're almost there. I'm going ahead. These might be dependent on the basis and the box. But insofar as these two things end up being the same, then that same value is going to be independent of the box and the basis. Okay? So let me finish writing this. I'm going to write it here. Let's continue the definition. Purely based on general principles, this is always going to be upper bounded by this, because this is a lower integral and this is an upper integral. If these two integrals end up being the same, the common value is called the Jordan content of S, and in turn, S is called Jordan contentable. Of S is called Jordan contentable. Okay, if S is Jordan contentable, then it doesn't matter which basis you choose, and it doesn't matter which box you choose. Meaning, if I were to choose some other box aligned with respect to some other basis, so let's think about this. So this was my first box, let's say. Okay, and I chopped this thing using aligned boxes like so, on and on, blah, blah, blah. You essentially count the number of boxes that hit this set. Then you do it this way. And you count the boxes that hit S again with respect to this different alignment. I'm telling you, insofar as Jordan content exists for S, these two numbers are the same, it shouldn't matter how you're chopping this. So for if the Jordan content for this specific set exists, this number is going to be independent of the basis and the box that you chose to even come up with these numbers. Now, at this point, you should feel a certain way. You should feel like something bizarre is going on. And there is something bizarre going on, indeed. So this is really the starting point of what is called measure theory. Remember, in week 1 or 2, I was discussing all of these different types of structures. I said for metric spaces too, we have the structure coming from the metric. We have the uniformity structure. We have the topological structure. These were just like getting weaker and weaker. And then I said, ultimately, underneath topology, there is the measurable structure. So this is really the starting point of the study of this measurable structure. And I thought, instead of going into details about this measure theoretical structure, it's better to keep this as minimal as possible so that we can start talking about vector calculus. Ultimately, because, well, one of them is that even though you can develop this content, all this stuff like they do in the textbook, this is not a very nice measure theoretical structure that you end up developing. So this, what I'm calling content here, is what is called a, from a measure theoretical point of view, something called a finitely additive measure. And finite additive measures are not the nice measures that are sort of standard issue for mathematicians. We want to be able to integrate things over regions, and we would like to be able to chop that region over which we're integrating into infinitely many pieces. This Jordan content does not allow that. It allows only finitely many choppings. And you're going to take, some of you are going to take more advanced analysis classes where it's going to be mostly about developing measure theory. Okay, so I thought to myself, first of all, this Jordan content is not as nice. It's fundamentally very buggy. Like things like this you have to worry about. And remember, we're not even talking about improper integrals. For improper integrals, we're going to have to do something else as well, which probably we're not going to do, just so that we can just focus on vector calculus. But when you switch over to this other way of doing integration, all of these things become a lot more natural, and it becomes a lot more useful. And like I said, for a modern mathematician, this measure theory stuff that some of you are going to learn later is really the standard issue sort of tools, whereas this is rather limited in application. It's still important, of course, that there are certain important ideas, but they are sort of more niche as far as I'm concerned. So right from the get-go, I designed this class so that I give you just a little bit of what this is all about. Don't go too much into details so that we can spend more time doing vector calculus. We can keep developing this and do fundamental theorem of calculus in this context also, but it's going to get more technical, and the flavor really changes, and it's not going to be very thematic as far as I'm concerned. So I decided I'm just going to give you the very basics. We're not going to go too much into details of these statements. So that's that. And yeah, so another thing is that I looked at other professors who taught this class before, and many of them, they just don't do vector calculus. They just focus on Jordan content. But I thought that's not quite right, perhaps, because I mean, in a calculus class, we should be covering some sort of fundamental theorem of calculus. And so I thought, well, if fundamental theorems of calculus are important, then that means we should be doing vector calculus, and we should not prioritize Jordan content. Anyway, so that's that. All this is to say that if you're feeling that there is something very bizarre going on underneath, there is, okay? Like the flavor really changes here. And specifically those of you who are going to go to grad school, you're going to take a class, a whole class and stuff like that. This is like how graduate level analysis starts really, understanding measure theory. How to even make sense of volumes in a nice sense. I should also mention, in the textbook, they just write this as V of S. But I'm explicitly writing something that is looking more jarring. Just to reiterate, this is not the same volume in a sense, even though it's an extension. And if you were to compute the Jordan contents of boxes, it's going to coincide with the volume. This is something defined more sort of like in a more complicated manner, you see. Like in this, there is at least two limits, right? So even to define the lower integral, we took, what did we took? A sup. Oh, we took the inf for a given partition to get the lower sum. And then we optimized, we took sups over those lower sums. So this itself involves two limits in and of itself. Whereas the volume of a box, it was a purely linear algebraic thing. We didn't do any limits. It was relatively easy. I just want you to keep that in mind, that this is a lot more complicated than just volume. And there are many other sort of notions like this, more measures that end up giving you the same volume for boxes, but for other sets, give you some other things. This gets very complicated. OK. So that's that. Any questions about this? I guess I should give you as an exercise. So any beta-aligned box relative to any basis is Jordan contentable, and the Jordan content of this box will be exactly the volume that we defined. What else? If I have finitely many Jordan contentable sets, their union too is going to be Jordan contentable. If I have two Jordan contentable subsets, their intersection is going to be Jordan contentable. There are these kind of things. OK. So now that we have this, we want to define integrals of functions defined on Jordan contentable boxes, Jordan contentable sets. By the way, with this, now we have handled 1 and 2. We're gonna get there in a second. Let S and V be a Jordan contentable box set. And let's let f be a bounded function defined on S, taking real values. Well, what am I going to do? I'm going to take the product of f with S and stuff. So, yeah, let's write it like this actually. Yeah, basis be a beta aligned box containing S then we define the lower and upper integrals of f. And likewise the regular integral as well. To be this, that's the lower integral. The upper integral is the other way around. Okay, and I call f integrable on S insofar as these two are the same. And just like in this case, for Riemann integrable functions, it's not going to matter with respect to which basis your box that includes the set over which you're integrating. So it doesn't matter what you choose as B or beta. Again, I'm going to leave it as an exercise. And even though I'm leaving this as an exercise, it's a painful thing it's going to be a painful thing to verify, actually. The proof of this is not going to be pleasant. It's going to be rather, it's not very complicated, the idea, but managing the epsilons is going to be slightly complicated, I think. So if f is integrable, then its integral is independent of beta and b. Of beta and b. What that really means is that if f is Riemann integrable in one of these senses with respect to some beta and some box, then it's going to be Riemann integrable with respect to any other basis and any other box. And furthermore, the integrals are going to be the same numbers. That's what I mean. You see, this Jordan content is rather clunky. When you do this measure theory the way you do in grad school, you don't deal with any of this. It comes out very clean. Okay. So that's that. We have integrals over contentable boxes, contentable sets. And in the text too, instead of saying contentable, they call it Jordan region. It's the same thing. OK. What else do I want to do? Yeah, I guess let's move over to vector-valued functions. Essentially, I'm going to just focus on functions taking values in finite dimensional vector spaces, normed spaces, really, so that I can talk about bounded sets, bounded functions. I don't need to, for the output space, I don't need to assume finite dimensionality, really. But there is something called, like there is some technology that we would need to develop to make sense of it, so that the output being a finite dimensional normed space is going to be essentially for convenience. So let S in V be Jordan contentable. Remember, V is always a finite dimensional inner product space. For the domain, for the input space, I really need an inner product, the way we're developing integration, so that I can intuitively make sense of volumes of boxes. OK. And let's let W be a finite dimensional normed space. Let me let F to be a function that is bounded from S to W. What does this mean? It means I take this set S, look at its image under my function f. That's a subset in W. I want that subset to have bounded diameter. That's what it means for a function to be bounded. I would like to define essentially all of these notions for a function like this. Well, what am I going to do? I'm just going to take a basis. It's not going to be dependent on the basis, the values of these things. But when you have an abstract finite dimensional norm space, what you do typically is you do something relative to some basis, and then you verify that whatever you did was independent of the specific choice of the basis. So let gamma be a basis of W. OK. This theory is so clunky. OK. So we're going to do it like this then. Lower integral, well, what is it going to be? It's going to be the tuple consisting of the lower integrals. In other words, this is going to be just this. Okay. What does this mean? Well, relative to this specific basis, I can write f as a tuple of m functions. It's going to have m components. These are going to have real values. And so these I can lower integrate, upper integrate, whatever. All of these is going to give me a number, and I'm going to put it into a linear combination. And that's going to give me a vector in W. That's how you do it. Same thing with the upper integral. Look at the coordinate representation. Look at its ith coordinate. That's a real valued function. Look at the upper integral of that. That's going to give you a number. Put it in the linear combination. OK? And again, I'm going to define f to be Riemann integrable insofar as these two vectors are the same. So you see this is a vector now. It's a vector in W. This is also a vector in W. I can ask if they are the same vector. So all the usual statements are correct. Any continuous function from S to W is included. Yes. At least insofar as S is compact. Never mind. All of these are bounded functions. This is closed under the C0 topology, and the Riemann integrals is a bounded and linear operator from this space to W. All of these things are the same. What else? If I were to take a Riemann integrable function and then take a continuous function defined on W, the composition would be Riemann integrable. I have the nice bound. Perhaps this is a nice thing to state as an exercise. Let's say I integrate like this. That's a vector in W. I can take its norm. Remember, norms are continuous functions. This should be upper bounded by the integral of the norm. As expected. What else? Well, if I have, let's say, two functions, both vector valued, defined on the same set, and a bilinear transformation that allows me to combine these two, then the output should be also integrable. Maybe that's a nice exercise, actually. Just to reiterate this multilinear algebra stuff a little bit. If f1 is Riemann integrable on S, taking values in W1, and f2 is Riemann integrable on S, taking values in W2. And if I have a bilinear transformation from these two spaces into some other finite dimensional norm space, then B of f1, f2 should be also Riemann integrable. So this is like the multivariable generalization of this idea that the product of integrable functions is integrable. And while it's perhaps good to try to prove these exercises, I think at the very least I want you to develop this idea that, I want you to have some intuition as to how integration should work. And based on that, I want you to be able to sort of guess. And like I said, there are certain pitfalls involved with whenever you're sort of looking at these contentable sets beyond boxes. And we're going to unfortunately have to look at these contentable sets because of this issue of diffeomorphisms changing boxes into more complicated things. But for instance, one of the things we're going to have to establish is the fact that the image of a box under a diffeomorphism is going to be contentable. Okay? That's going to be important for change of variables, for instance. One theorem that I'm not going to prove, that is in the textbook, is this. It gives you a condition that really is not that useful as it seems like in practice. For a subset to be contentable, namely, you would want its boundary, in the sense that we discussed a long time ago, to have 0 outer Jordan content. So let S be bounded. It's a bounded subset. And S is Jordan contentable. If and only if its boundary has 0 outer volume, outer Jordan content. So Jor overline n, and then the boundary of S is 0. So if something goes wrong, it goes wrong in the boundary. I hope at the very least I can convince you that this is correct, because at least for boxes, any one of these, so the boundary of a box is going to be a union of boxes of lower dimension, meaning if I start with a 2-dimensional box, its boundary is going to be a union of 1-dimensional boxes, that is to say intervals, and therefore it's going to have, so this boundary is going to have 0 2-dimensional volume. Okay, so at the very least, that's sort of like an intuition. I'm not planning to prove this, but if we end up having time, we can go back to it. Okay, I think that's going to be it for today. Thank you. I'll see you on Monday.